The theory which we have developed so far, we will now try to apply that by solving some well-known examples. The main idea is to get proper understanding of the theory of elasticity based on isotropic material. So we will start off with an example of a circular cylinder which is of length L and is subjected to torque at the free end of the cantilever. We will assume that the material constants are already known, and we will try to find out the expressions for stresses, strains, and displacements. We will try to solve this problem using the so-called displacement formulation. In our previous presentation, we discussed that in the case of displacement formulation, we have to start from displacement. After displacement, we'll find out the strains, and then from there onwards, stresses. Since we are already starting from displacements and the strains are worked out based on actual displacements of bodies, we don't need to satisfy the compatibility equations. Or in other words, that is automatically satisfied. We will assume that the body force is equal to zero and there is no acceleration of the body. Thus, we are dealing with quasi-static problem. Let us write now the displacement vector. We have three components of displacements. One is UR, another one is U theta, and the final one is UZ. As we have a cylindrical body which is subjected to an end torque, this type of problem can be easily solved using the cylindrical coordinates. We already have derived the equilibrium and strain components in terms of cylindrical coordinates. Just to remind ourselves, we take a cylinder and extract a piece out of that cylinder, which is shown over here. This piece has got four sides numbered as 1, 2, 3, 4. In this problem, we can have three distinct components for displacements and forces. One component will be in the radial direction, another component will be in the circumferential direction, and the third component will be in the longitudinal direction. The longitudinal axis will be considered as Z. The radial stresses and strains will be represented by sigma or epsilon r, and the circumferential stresses and strains will be represented by sigma theta or epsilon theta. Beside axial stresses and strains, we would have shear stresses at the sides also. In our previous presentations, we derived three equilibrium equations in terms of cylindrical coordinate. So this is the first equation, which is trying to equilibrate all the forces along radial direction. We have got the second equation, which is shown here, and this is trying to equilibrate all the forces in the circumferential direction. The final equation is trying to equilibrate all the forces in the longitudinal z direction. We also discussed the strain components in cylindrical coordinates. The radial strain was worked out as partial u by partial r, where u is the displacement in the r direction. The tangential strain was worked out as u by r plus 1 by r partial v by partial theta, where v was the displacement in the circumferential direction. The longitudinal strain was worked out as partial uz by partial z, uz being the displacement in the z direction. Similarly, the shear gamma r theta was worked out as partial u by r partial theta plus partial v by partial r minus v by r. The shear strain gamma theta z was worked out as partial uz by r partial theta plus partial v by partial z. Finally, the shear strain gamma rz was worked out as partial uz by partial r plus partial u by partial z. So in the case of displacement formulation, we have to first of all find out the displacements. The displacement vector comprises of ur, which is the displacement along r direction, u theta being the displacement along the circumferential direction, and uz is the displacement in the longitudinal direction. All three of these displacements can be a function of r, theta, or z. Now, we will have to make some assumptions which will simplify our problems, because if we don't make any assumption, it will make the problem almost intractable. The first assumption is that ur, which is the displacement in the r direction, is 0. ur equal to 0 means that there is no displacement in the r direction when the cylindrical body is subjected to torsion. Similarly, we assume that the applied torsion will not cause any displacement in the z direction. Hence, these two displacements can be knocked out. We will now investigate what will happen to the circumferential displacement u theta. The circumferential displacement can be a function of radius, theta, and z. Z is the longitudinal axis, theta is the rotation, and r is the radius. In the case of this cylinder, where we have applied torque T at the end at particular distance z from the origin, the angular displacement u theta will be 0 at the center of the cross section and will keep on increasing linearly. So, for example, it is the same cylinder where torque T has been applied. We can divide the surface of this cylinder into longitudinal and circumferential elements. So we will get elements as shown in this figure. Before deformation, all these elements will be meeting each other orthogonally. So these small boxes will be like a rectangle. After application of the torque, the circular rings will stay circle, but the longitudinal lines would be twisted as shown. For a particular cross section, if O is the center, as we move away from our center, our u theta, which is the tangential displacement, it will keep on increasing linearly. So if we have torque applied, u theta along the radius will increase linearly, and it will be 0 at the center of the cross section and will increase to a maximum value at the surface. So surely we have u theta dependent on radius r. U theta is also dependent on z, as we can see that a fiber initially before deformation shown as O-A-B-O in red will twist into O-A-C-O after deformation. Thus, u theta at the fixed end is 0 and u theta will keep on increasing and reach a maximum value when we come to the end of the cantilever, or in other words, at the free end. Thus, u theta is a function of z. Now let us see whether u theta is dependent on theta or not. As we discussed, we can divide the whole length into longitudinal lines and circular lines. When When we apply a small torque, the circular line will remain circular. However, the longitudinal line would twist, as is shown in this figure, where a line initially straight has twisted. Thus, at the support, the twist is zero, and as we move away from the support, the twist keep on increasing. Important thing to note is that the circle will stay circle after deformation, so there is no warping allowed in this cylinder. Thus, we can say that at the most, because of u theta, the circle can rotate, but there won't be any change in the circumferential deformation or u theta. From this argument, we can say that u theta is not dependent on theta, and we can simply equate it to a function s, which is a function of r and z, or dependent on r and z. Thus, our u vector is now ready. As we discussed previously, after working out the displacements, we have to find out strains. In our previous presentation, we discussed strain components in cylindrical coordinates. We worked out all the strain components corresponding to the cylindrical coordinates. All these strain components can be written in the form of a tensor, and after that we can work out all the components. For ease, we have written all the strain components over here. So the strain components comes out to be 0, half, small bracket, s comma r minus s by r, 0. Then 0, 0, half, s comma z, and then a symmetrical matrix over here. Please note, this first component, epsilon r, is equal to partial ur by partial r, and partial ur is 0. Hence, the first component of strain is taken as 0. The second component, which is r theta, is partial u by r partial theta plus partial u theta by partial r minus u theta by r. Please note that according to the convention of this example, u is equal to ur, v is equal to u theta, uz is the same as uz. So all these strain components which are taken from our previous presentation, we can change the symbols accordingly. Thus, partial u theta by partial r is s comma r. Partial ur by r partial theta is 0 because ur is 0. And v by r is equal to u theta by r, and that has been written over here. So we can plug the values in these strain components and get our strain tensor. After that, we can use the constitutive equation in the constants lambda and mu. This equation we derived in our previous presentation. Please note that in this question, we don't need to simplify it either in plane strain or plane stress. We can just use the previously developed constitutive equation. Thus, our stress tensor will come out to be 0. Thus, the components of stress tensor are shown over here. In this equation, epsilon v is the volumetric strain, I is the identity matrix, 2 mu is the constant, and epsilon is the strain tensor, which is shown over here. Plugging the values, we will get the tensor in the form shown. Now we can apply equilibrium equation. So first of all, we started off from displacement, found the strains, from strains we found the stress, and now we are trying to apply the equilibrium equation. We know that we have got three equilibrium equations. The first equation is automatically satisfied if we plug the same component of stresses as derived. So the first term, which is partial sigma rr by partial r, that is 0 as shown over here. The second term, partial r theta by partial theta, is equal to 0 because no theta appear in this equation. Similarly, the third and the fourth terms are also 0. So this equation is automatically satisfied, and so is the equation number 3 of the equilibrium. It's only the second equation which is not satisfied and which has to be enforced. So rewriting the second equation and calling it A. After this, we can find out the sigma theta r, which is mu s comma r minus s by r as per the stress tensor we have derived. Sigma z theta is mu s z s comma z. Sigma, we can partially differentiate sigma r theta with respect to r and sigma z theta with respect to z, and put the values back in this equation. Thus, we get s comma rr plus s comma r by r minus s by r square plus s comma zz equal to 0. Mu is taken as common and taken out. Now, this is clearly a partial differential equation. We commonly use separation of variable technique to solve partial differential equations. So we have got a function s of variable rz equal to ur and v of z. Thus, we have separated this function into two variables. One variable is u of r, so it is exclusively dependent on r, and the variable v is exclusively dependent on z. Now, we can differentiate this twice with respect to r. Now, this function can be differentiated with respect to r twice as per the partial differential equation A. Then it can be differentiated once with respect to r and divided by r minus the same function by r square plus this function differentiated twice with respect to z. So after performing the required partial differentiation, we get the equation as u double dash v plus u dash v by r minus uv by r square plus uv double dash equal to 0. We can separate this into two variables, one in u and another in v. Thus, separating u and v terms, we can see that the summation of these two terms is equal to 0. We can call this whole u term as minus k and this term of v as k. Now, we have to find the value of k. First of all, let us take this function. This is v double dash by v is equal to k, or v double dash minus k times v equal to 0. So this is the second order linear differential equation. This type of equation is called as a homogeneous linear ordinary differential equation with constant coefficients. So as we can see, this is a ordinary differential equation and its coefficients are all constant, and it is homogeneous because right hand side is equal to 0. So this is the same form as given over here. We have got constant coefficients, we have got homogeneity, and this differential equation can be described generically as the one shown over here. Now, in order to solve this ordinary differential equation, we convert this one into a characteristic equation. Then find out our lambdas. So we can have three cases. In the first case, we have a square minus 4b greater than 0. So a square minus 4b greater than 0. That is case 1. In this case, we will have two real roots. If a square minus 4b is equal to 0, we will have a real double root. And if a square minus 4b is less than 0, then we will have complex conjugate roots. So in the case of case 1, we can write y1 equal to e1 lambda 1x and y2 equal to e times lambda 2x. The function satisfying the ordinary differential equation, which is this one, would be c1 e times lambda 1x plus c2 e times lambda 2x. In the second case, our y1 is equal to e power minus a by 2x. Thus, in the second case, we have y equal to c1 plus c2x e power minus ax by 2. For case 3, which has got complex roots, its y is equal to e power minus ax by 2 small bracket a cos omega x plus b sine omega x. Now coming back to this question, we can have the same three cases. So if k is less than 0, we get our v equal to a cos omega z plus b sine omega z. In these solutions, it is important that we use appropriate engineering judgment to either accept or reject a particular solution. Thus, v is equal to a cos omega z plus b sine omega z shows that it's a periodic function. And in the case of torque, we can't have a periodic function. Periodic functions are common in vibration problem. However, we have considered a quasi-static problem. So therefore, this type of solution is not possible. So we will reject this based on our engineering judgment. Now, in the second case, we can have k greater than 0. And if k is greater than 0, as we said, we can have c1 e power kz plus c2 e power minus kz, the value of function v. Now, in this type of solution, the first thing is that our function, which is e power kz or e power minus kz, that is varying exponentially. Please remember, v is a function of z. We would expect that as we move away from the origin, v of z increase, but it should not increase exponentially. So therefore, exponential values cannot be accepted. The other argument is that if we put v at z is equal to 0 in our problem, we should get v equal to 0. And clearly, we get c1 plus c2 not equal to 0. If we take c1 as well as c2 equal to 0, then that would make this solution trivial. If we don't take them as 0, then it is not possible to have some value of v at z is equal to 0. In this figure, it is clear that there is no circumferential deformation at z is equal to 0. Therefore, this solution can also be rejected. So finally, we are left with k is equal to 0. Once we put k is equal to 0, we get a simple equation az plus b equal to 0. As we know that v should be 0 at z is equal to 0, that makes b equal to 0. And we get v is equal to a z. Now let us solve the u double prime equation. The equation u double prime plus u prime by r minus u by r square is of the form of Euler-Cauchy equation. As per this equation, we can have again an auxiliary equation in terms of m's, and from there we can either have real and different roots where y would be equal to c1 x power m1 plus c2 x power m2, or we can have a real double root where y would be equal to c1 plus c2 ln x small bracket times x power m. In our case, we can again have a characteristic equation we will find a real double root. We plug the value in our u of r, and we find that our u of r is equal to c1r plus c2 by r. Now, the displacement u along r is shown over here, and that should be varying linearly. 0 at the center of the circle and reaching maximum at the surface. According to this equation, if we put r is equal to 0, we will get infinite. Our second term will become out of bound. Therefore, we can make C2 equal to 0 and UR equal to C1R. Thus, we have found the function U of R and V of Z. Now combining it, we get S equal to C1RAZ. C1 and A can be combined into a constant alpha RZ. After this, we can find out our strain components and our stress components as shown over here. The epsilon r theta comes out to be 0. The sigma r theta comes out to be half alpha r, and sigma z theta comes out to be mu alpha r. From sigma z theta, we can see that it is 0 at the center, and sigma z theta varies linearly as we move to the surface. And this is what we said over here, that it should be 0 and should vary linearly as we move to the surface. Now the final constant which is left is alpha. This alpha can be worked out by considering the boundary conditions. So for example, if we have this body, known and twist is applied at the free end of the cantilever, then we can say that the end rotation is beta times r, where r is the radius where we are applying the angular displacement beta. So our circumferential displacement is beta r, which is got from the load application. And this beta r is applied at z is equal to L. Now u theta, as we discussed, is equal to alpha r L, taking z is equal to L. Comparing both of these equations, we get alpha equal to beta by L, and alpha is called twist per unit length. Now there can be another scenario where we apply a torque. In the case of torque, we exactly don't know where we apply the torque. So we can have an instrument which holds the surface and then apply a twist, or we can have a small portion of a cross section, and that on that portion a torque might be applied. Thus, we can have a clamp applying torque at the surface, or we can have a small portion of the cross section with a torque applied at a point. If we are applying torque, we will have a region of disturbance or stress concentration at the point of application. Over here, it is important to mention what is called the Saint-Venant principle. Saint-Venant compatibility principle states that the effect of change of load or boundary condition become negligible at a sufficient distance from the point of application or the region of interest in a structural element. In other words, when a force or moment is applied to structural component, the stress and deformation caused by that load becomes more uniform at a distance away from the point where the load is applied. Thus, if we apply direct torque over here close to the region where we are applying the torque, we will have high disturbance. But as we move away from this region, the effect of this applied load will become smaller and smaller. At sufficient distance from the disturbance, we will have no effect of that disturbance. Based on Saint-Venant principle, we can say that the applied torque won't be of concern to us as we are deriving all these expressions for the region where we don't have high stress disturbance, where the effect of the load application or boundary condition have become neutralized. So this is called static equivalence. The application of Saint-Venant principle is called static equivalence. Thus, our torque is equal to sigma z theta, which is the internal stress, times r d theta integral, and that integral have to be applied from 0 till 2 pi. Thus, putting the value of sigma z theta, which is mu alpha r, and multiplying the stress with an area 2 pi r dr, we get 2 mu alpha pi r cube dr. And finally, we reduce this to alpha mu pi c4 by 2, c being the radius of the cylinder. Pi c4 by 2 is called polar moment of inertia. So from this, we can get our alpha equal to T by mu j. Thus, sigma z theta is equal to mu T by mu j gamma, or T gamma by j. We can also write this in the form of T r by j. Thus, sigma z theta is equal to T r by j.